Saenko. She's currently an associate professor at University of Boston, where she focuses on machine learning, computer vision, human-computer interaction, and she will be presenting her talk, Explainable AI, and why we need her. Thank you very much.
Thank you. Can everyone hear me if I talk at this level, or should I? Yes, back row is good. Awesome. So thank you so much for coming to the workshop and coming to my talk. Why do we need explainable AI models? Of course, we all know what AI models are, but how many people have heard of explainable AI or XAI? Okay, quite a few people. Good. Maybe that part can be shorter, the motivation part. But so actually, I kind of like this picture because if you look at it, you can kind of understand what it is. But does anyone know what these structures are? Solar panels. Yeah. I think so. I don't know. Yeah, actually, I'm pretty sure they are solar panels. But sometimes when we look at an image, it's not clear why or what is in it. So here's an example of an image from the data set called Functional Map of the World that has a lot of overhead imagery of various landmarks. Like in this case, there's some kind of landmark, and it kind of looks like maybe it's some solar panels. So if we apply the deep neural network that's trained to classify these types of landmarks on this data set, in this particular case, it predicts, in fact, solar farm with 63% accuracy. It also predicts shopping mall with 23% accuracy. So, seems like a reasonable answer, but we might want to know, well, why does the network actually think that this is a solar farm? Or what about this picture led it to believe that it might be a shopping mall? So that's why we need explainable AI, so that we can explain the prediction of the neural. Of course, we can rationalize as humans why we might make these decisions, but how do we know why it's really predicting this thing? So here are some explanations generated by one of our recent models that I'll talk about today. The first one is for the category solar farm, and you can see that it actually, so here, hotter colors means more important for the network decision. So here you can see that it's actually looking at the part of the white building that kind of looks like solar panels, perhaps, and that is the most important part of the picture. But if we ask it to explain its decision for shopping mall, then it highlights other areas, particularly more of the parking lot and also some part of the highway. So potentially it's learned that shopping malls are often near highways. Here's another example. This is an image from the Pascal data set, and here a model, not the same one, a different one, predicts car with 64% accuracy. So why do you think it might be predicting car? Well, let's look at the explanation. So in fact, the main reason seems to be because of this monitor sitting in the middle of the street. Even though there are some cars parked on the side, but it mostly seems to be using the monitor and the context of the street, right? So sometimes we want to use explainable models so that we can understand why they're making predictions, actually improve them, and maybe have them rely less on context to make certain decisions like this one. Here's another one. Here, the classifier prediction is cow, whereas in fact these are sheep. So again, if we look at the reason as generated by our method, we see that in fact the model seems to have a bias and is mostly looking at the black sheep to predict that it's a cow. And it turns out that in this data set, most sheep are white, which is also true in the world. But because machine learning models tend to rely on bias in training data, they tend to exaggerate bias in training data, the model seems to have learned that black sheep or black kind of animals that look like that are cows. So it mistakes this for a cow. Here's another example from a paper that we have at this conference called Women Also Snowboard. And here, this is actually a captioning model. So it's taking an image and predicting a caption. In this case, it predicts a man sitting at a desk with a laptop computer. But when we look at the reason, we see the reason for the word man. Why is this network predicting man? We actually see that it's not really focusing on the person. So we might think, well, it's detecting the gender incorrectly, but in fact, it's not even looking at the person. It's just it detected a computer, and it decided, because of the training data bias, that the most likely way to start that sentence is that a man is sitting at a desk with a computer. And then this is a model that we've solved. I won't talk about this model today, but we actually in this paper have an approach that corrects for this type of bias. And this is the caption generated by our model, which is correct, and it's actually now looking at the right place when generating the word one. So I encourage you to attend those if you're interested. Okay, so today what I want to talk about is sort of three main things, or two main things. One being, how can we explain black box models, like black box neural networks specifically? And then also, once we have explanations, how do we evaluate them? How do we know what's a good explanation? And then I'll also talk about an alternate approach where instead of taking a black box neural network, where by black box I just mean that it's some arbitrary structure, architecture, parameters, we don't know anything about it, we just know the input and the output. But rather than that, what if we could actually design our own neural network structures that are inherently more explainable, so they're naturally revealing in a way that's interpretable to humans how they make decisions. All right, so let's start with explaining black box neural networks. So again, if we have an image classifier and we feed an image like this, and let's say it predicts the class lion with 94% confidence in this case, we might want to ask why, what makes this image look like a lion to the model? Of course, to us, we can all guess why we would say this is a lion, but to the model. In particular, we might want to ask, well, does the lion cub contribute to that decision? Or what about the reflection in the water? Excuse me. Does that contribute to the decision? So we propose an approach that can explain, in terms of the saliency map, what is the most important pixels of the image for that particular decision. And we see from this explanation that, yes, the lion's face contributes, the lion cub doesn't really contribute much, and the model doesn't actually see any lions in the water. So there's some pretty great work already in this field of explainable artificial intelligence, or XAI. In particular, there are some models that try to explain or visualize what a convolutional network has learned by applying activation maximization. So for example, what's the image that would maximize a given network's activation for ostrich, or prediction of ostrich? So these are some nice early works. This is from Eichler 2014. Then a little bit more recently, people have used generative networks to actually generate a more realistic-looking image that visualize what a network might predict. In this case, volcano. This is an image that the network thinks is a volcano. There's also alternative approaches that do things like network dissection, where we look at specific neurons and see what kind of features of the image activate specific neurons. Like this particular one is a neuron that seems to be activated by pictures of cars, or parts of cars. So we have more understanding what different neurons are predicting. And then there's a class of interpretable models, which is what I'll talk about in the last part of my talk today, that actually try to expose some of their their structure in their own decision making. This is a modular neural network that tries to predict the answer to the question based on the image by kind of decomposing it into subtasks and solving each subtask in sequence, and you can see the intermediate decisions. So interpretable models can expose the intermediate decisions along the way to the final decision. But first, I wanted to focus on this one kind of explanation, which is a saliency map. So a lot of the methods out there are detecting saliency maps to explain a network's decisions. So, for example, we can do this for image classification. Like this is an image of a goldfish, and this is showing the saliency map predicted by our method for explaining the prediction of goldfish. You can also do it for action recognition. For people have done it for text, for image captioning. Right. So for text, Y is predicted as a positive sentiment. What part of the sentence we also highlighted using a saliency map. So, of these existing approaches to saliency detection, most of the current ones assume a white box based model. So by base model, I mean the model we're trying to explain. So they assume the base model that is white box, so we have access to the parameters and the architecture, and we can look at the gradients for a particular input, right? So excitation, backdrop, radcam, all of these are examples of white box explanation models. But what we're interested in is, what if we have a black box model that we don't have access to the internals of the model, we can only put input and output. That's useful often, right? Because sometimes we just don't have the model, or maybe we just don't want to spend additional time implementing. And also, we need to know some heuristics about how to combine gradients, actually how to use the gradients and the parameters of a network in the white box case to best generate the saliency map. So these are two main prediction methods, saliency map detection methods. Sliding occlusion, where you occlude part of the image and you compute the activation and use that to predict the saliency map. And another method is line, which you might have heard of, which also is a black box method that works by using pixel segmentation, pixel segments or superpixels, and learning kind of a local linear model for this particular input image and classification decision. So you can kind of see one of the downsides of line is that the superpixels may be inaccurate and noisy, and it does rely on superpixels. So that is one of the negative aspects of that model. So we proposed a different approach for black box model explanation that we call randomized important sampling. This is work of my student Vitaly Kutsuk with my postdoc Abir Das, and this was presented at BOVC just last week. So what we do is we assume the black box, that we're given the black box model F, and we have some image I, and we know what class we're trying to explain. And we generate a mask. So we generate a mask that we multiply with the image so that it looks like that, and then we feed that masked image to the black box. And then we measure the prediction for that particular class. So if we feed this particular masked image, then the probability of shark goes significantly down because the mask occludes most of the shark. Now we keep doing this, we repeat this many, many times for different randomly sampled masks. And then we use a weighted sum of these maps, weighted by the prediction probabilities to compute the final saliency map. So this is an extremely simple approach. It's similar to the sliding window method, but the nice thing about this is that we can estimate saliency for regions that are farther apart, that are not just localized in the image. So that, for example, that picture I showed of the fish, where there are multiple fish, and if you only include one fish, then the classifier might still predict fish for the whole image because there are other fish still not included. So this is estimating better non-local saliency map than the sliding window method. So so basically, what we're doing, we can think of as randomized input sampling, where the saliency S of some segment lambda is estimated according to this expectation. So we can think of it in terms of this expectation, except we are using continuous masks instead of binary, and we're also using an approximation to expectation by doing Monte Carlo sampling. So to generate the masks, we start with binary masks, but then we upsample them in a way that makes them continuous, and then we also do random crops from masks. So this is all done to kind of prevent hard edges being introduced in images, because if you multiply by these hard edge binary masks, you end up with some hard edges in the image, and that sometimes confuses the model, introduces extra gradients into the image that confuses the model. Then we repeat this process at times to generate the mask. So here is another explanation. This is to illustrate that we can explain for the same image different categories. So this particular image, we can explain the prediction of sheep, which falls on the white sheep, and for cow, it falls on the black sheep. And this goes back to this problem with this particular data set that all sheep are white. Okay, so how do we now evaluate, now that we can generate these masks, how do we evaluate how correct they are? So the main approach for evaluating saliency maps so far has been to use localization metrics, where we have some ground truth bounding box for each object that we're trying to explain, and then we compare the saliency map to that. But this has some downsides. So we also use causal metrics, so I'll explain what I mean by that. So first of all, for localization metrics, sometimes they're actually not what we want, because, or arguably, because let's say we have this image, this is from the functional map of the world data set, and the prediction is wind farm, and a bounding box around the wind farm would only explain, would only contain the actual, this white object, this windmill, but as you can see, the shadow being cast by the windmill seems to be very important according to this explanation. So what is the true answer here? And we ultimately don't know, because as humans, we can't explain what a neural network is thinking. It's just millions of mathematical operations, and it's very hard for a human to understand what it's actually doing. All we can do is rationalize. Well, if I were to predict this was a windmill farm, then I would focus on this part, or I would focus on the object. But even we ourselves don't know how we make decisions, right? So why did you get up this morning, and why did you have a particular item for breakfast, or why did you have wear particular shoes or clothing? You can rationalize why you made those decisions, but ultimately we don't know how the brain works. So it's very hard for us to similarly know how a neural network works. So in this case also, this explanation for recreational facility, we might use this bounding box for localization metric, but in fact, maybe this is a better explanation, because looking at the green part of the stadium and not looking at this part that's occluded by shadows is a more correct way of interpreting what the model is doing. So for that reason, we introduce this metric called deletion, and another one called insertion. The idea is very simple. Given an explanation like this, we occlude parts of the image, starting with the most salient and then including more and more of the pixels in order of decreasing saliency. And then we measure the probability of the class for each occluded image. Right? So you can see that for this image, it starts at 80% probability, and then it goes down to almost 0. And what we want, what we argue is a good explanation, would produce a very sharp drop-off. So it would generate a saliency map that would occlude exactly the minimal number of pixels that will get the model to stop predicting that class, right? So parsimony or the minimality, we argue, is a good thing for explanations. Okay, so then the area under curve, the smaller it is, would be the better. And then similarly, we do insertion where we do the same thing, but now we're introducing pixels from highest to lowest saliency. And here, we actually introduce them onto a blurred image because we find that this actually produces higher scores overall for all models. The reason might be because when you introduce onto a blank background, you might be, if saliency maps kind of are shaped as objects, the network often thinks that there's a balloon there, right? So if it's a round kind of or circular saliency map or round shapes, it often will hallucinate balloons and things like that. So it's kind of, this is actually a hard problem, right? How do you correctly do this? How do you correctly measure if an explanation is correct? So this is the approach that we've come up with. Okay, so here's a qualitative example for this goldfish image. This is saliency produced by our method. This is GradCam, and this is Lime. So in this particular example, GradCam focuses mostly on this region and Lime as well, whereas our model picks out several of the fish. So again, we don't know if this is correct or not. So we're going to evaluate this using our deletion and insertion causal metrics. Okay, so these are the results. So here for these metrics, lower is better for deletion and higher is better for insertion because they're the opposites. We see that our model does pretty well and better compared to existing models, of which GradCam and GradCam is not a black box model, but sliding window and Lime are black box models. So we also compare with localization metrics using this kind of pointing game where if the saliency map points inside the bounding box, the ground truth bounding box, then we deem that to be correct. So it's a looser metric than having the map correspond exactly to a bounding box. It's just the pointing inside the bounding box. And so we also tried this, I think I forgot to mention this is on ResNet 50 and VGG16 models that we're explaining and on the ImageNet dataset. This is on MS Coco and Pascal, also for the same two models. And we can see that our method is not always the best here. And in fact, you can think of it in the sense that if a model, if the base model like VGG16 is very good at mimicking human explanation, right? So it's always actually using the right object to predict that that's the object and not some background part or some random part of the image. Then the localization metric should correlate with what the model is doing. But for a model that makes mistakes, then some of the decisions can't be explained very well by localization metric because it won't agree with the ground truth, even though that is, maybe the model is using the background to make that decision. Okay. So here are some more examples from FMOW. The top one is a racetrack, and that's the explanation for it. The middle one is a lighthouse. So the first column is the explanation for lighthouse and racetrack, and then the second column is for some other class that I can't quite see. Fountain, so that's the explanation. Park. So this is explanation for park, and this is explanation for fountain. You can see it's actually looking at the fountain. All right. Any questions? Yes.
This deletion metric looks very similar to the way how you generate the silency map.
Right.
Does it make a fair evaluation?
That's a very good question. I happen to think that using optimizing the actual metric that you're evaluating with is a good thing in general in machine learning. But yeah, it's a good question. Maybe it's not fair because some other model will optimize some other loss, right? But I think intuitively the deletion metric makes sense, at least, right? So if you're deleting part of the image or inserting parts of the image, it makes sense that those are the parts that should give you the best explanation. If you remove some evidence, then that evidence shouldn't contribute. So to me, it makes intuitive sense. But yeah.
Yeah. You do this for all the categories that are not in the image, because otherwise you don't know.
So when we do the quantitative evaluation, we only do it for categories that are in the classifier. Yeah. But yeah, I'm not sure how you would do it for categories that are not part of the classifier.
I mean, if you have the animals in the image, do you do it also for bicycles, which is in the classifier?
Well, so if the classifier can predict bicycle plots, yes, we can also explain bicycles. Right?
But on the image that has no bicycle.
Yeah, we can still find evidence. Yeah, we can force the model to tell us what would be the evidence for predicting bicycles. Any other questions?
Okay, so just before the next question, I'd like to thank you and just take the very last question, and at the same time we'll do the computer transfer. But,
okay.
So just the very last question.
So I'm actually not quite done. I'm just.
Oh, sorry.
5 more minutes. I'm so sorry. I'm sorry. Yeah, I know it looks like I'm done. Okay, maybe. Yeah, I only have 5 minutes left, so maybe let's move on very quickly to talk about explainable networks that we can design to be naturally explainable. All right. So sometimes the decision process can't be explained by a simple saliency map. For example, here this is from the Clever data set. The question is how many other things are of the same size as the green mat ball, and when we're answering that question as humans, we're actually looking at different parts of the image, right? We want to find the green mat ball, and we want to find things that are the same size, so probably our gaze is moving around. So we can show all of the objects that we looked at, but that doesn't quite explain the process, where we looked at first, what we looked at next. So how do we explain models that make these kinds of predictions? And ordinary convnets struggle with this because they have a hard time representing different computational steps separately. There's one convnet, and stuff happens, neurons activate, and it's hard to know what corresponds to which part. Is there a compositional reasoning process going on there? And so there's an alternate approach of coming up with compositional neural networks. So they're called neural modular networks. And what they do is they actually decompose the network itself into subnetworks that corresponds to some subtasks, like find something, relate, or compare, count. So each module of the network actually does a separate task. So this is actually a way to explain the model's decision, because we can visualize the output of each intermediate module. So let's see how it handles this particular problem of this example. So first, a neural modular network will apply some attention and predict what is the most important part of the text, and here predicts things. That's offset. Green mat ball. This should be green mat ball. And it also predicts the next module to use, and here it predicts find. So it applies the find module, which just detects things given the text. So it's going to detect the green mat ball. And this is the output, which is an attention map. And we see that, in fact, for this image, it did output the green mat ball. It did find the green mat ball in the image. Now we can see that it focuses on the right object, so we kind of can tell, okay, maybe this model is on the right track, because it should be looking for the green mat ball. So then the output of this find module is stored in memory, and we implement it as a stack. So we push the output onto the stack. And the model predicts the next module, which in this case is relate, and the text attention is same size, so it's looking for things that are same size. In this case, the object of the same size is the green mat ball, the prediction of the first module. And that's the output, so those are the things it found from the relate module. And then the next module predicted is count, and the text is how many other things. And the output is 4. So do you guys think that this particular run was made sense intuitively? It does, right? That's kind of how we would approach this problem. So this approach supports more complex questions like we see here, and also works on natural images. This is an example from the VQA data set. So because I sort of had too much fun with the first part and ran out of time, I'm going to skip quickly through this. So basically, the prior work on neural module networks is done by learning with a known layout, and that's easy, right? Because we know what the right layout is of the network, what the modules are. The main contribution of this work, which is presented here at this conference, is to propose, first of all, fully differentiable neural module network, and also learn them without the ground truth layout, so that we don't know what the right modules are at training time. Okay, so we don't require expert layout supervision in this work. All right, so let me just show you some nice outputs. Here, so we also can apply it to multiple tasks. The top is for question answering, and the bottom is for referential expression grounding. So this model, the same model, can solve both tasks, and it figures out what is the task that it's being asked to solve automatically, and then predicts a different answer, either yes or an answer to the question, or it predicts a bounding box for the expression task. And it shows all the intermediate steps. So I won't go into the details of the model. I'll just show you how we evaluate this. So we did the quantitative evaluation just based on accuracy on Clever, and our model does quite well, not as well as using, so VQA accuracy on this is around 99%. If we use expert layout supervision, we get 96.6, but if we don't use expert layout supervision, we actually get something fairly high as well. And this is really the contribution of this work, is that not using layout supervision gives us, we close the gap towards getting the same accuracy as using layout supervision. And we also compared it, we also evaluated it with humans. And to evaluate with humans, we showed humans outputs of the model, but we didn't show the answer. Right, so we just showed the reasoning steps in the module outputs. And then we asked humans to predict what the answer will be. What is the model going to decide? And we also asked them, are the internal reasoning steps about clear and understandable to you? So I think this is the first time that this kind of evaluation has been applied to neural module networks. And we have some interesting results. For example, in this case, our model, which is the blue bar, is much more often rated as clear as opposed to the model that we're comparing, which includes MAP, which is a state-of-the-art model for this task. All right, so I'm really out of time now. So I'll end here, and do we still have time for questions?
Yes, let's take one question if anyone has any.
Makes sense to, I guess, train a model which is outputting a, say, class prediction, and at the same time trying to learn a mask so that it maximizes that. Or in a GANI way, try to have the model output its prediction and the salience of that at the same time.
Right. So I'm trying to think of GAN way. So what would the GAN be applied to? On the mask? I see. And so you would need some ground truth masks.
Yeah, I guess you could also do it just by random masking.
Yeah, I think this question in general of what is a good way to learn reasonable math? This is a very good question. So I think that's very interesting.
Okay, so thank you very much for your presentation. Thank you for your talk. And please